Ready now? Okay, so Chuck Weibel's going to talk about K-theory for newcomers, part 1.
Thank you. So the physical audience in this room is not the audience I'm intended to talk to. So I'm just assuming that people who I'm talking to have never heard of K-theory. So K-theory, a ring, the K-theory of a category, and finally generate a projective module. And sometimes you put a subscript on it and sometimes you don't. So I want to think of it as a spectrum. Which is kind of a topological space. And case of N of R is the homotopy group of the space. So there's a sort of a duality that's going on. There's an algebraic version, which is the homotopy groups, and there's the topological version, which is these infinite loop spaces or spectrum. So what's going on with K-theory there is a basic relation. The in K0, you have two projected modules. The direct sum of the K0 is the free ability group on the projected modules modulo this relation. And so this generalizes to symmetric binomial categories. Because a symmetric binomial category is exactly a category where you can play this kind of game. Well, okay, so I'm not interested in calculating this specific groups for a while. We can also talk about the end of a variety. That's the homotopy group of space again. Kx, K30, vector bundles on X. This is it generalizes to exact categories or abelian categories. Exact categories when we have an exact sequence like this. And you have a notion of short exact sequences. For an exact category is a subcategory, and an abelian category, which is closed under extensions. In other words, if A and C are in the subcategory, then so is B. Now, these are the two cases that I'm most interested in. We just keep going with things. If we take a category like bounded chain complexes over a ring or something like that, and you can talk about weak equivalences, which are quasi-isomorphic. Well, in this particular example, the quasi-isomorphism is what's known as weak equivalence. And then we get this category K, A. All right, so now at this point, I want to talk about models. K of R is going to be K0 of R cross EGL of R plus this due to Quillen. For exact categories, A of R, K of X is going to be loops on the suspension, Q of A. Also do equivalent where Q of A is a category. And some category. It's a category with particular properties. And since this is an introductory talk, I'm not going to tell you the details of what that is. So here we have construction, which is called the WS dot construction of good world housing. And so this is called wall as a game. So main theorem here is the K theory. Relative chain complexes of R. It's the same thing as the K theory of R up to homotopy equivalence. So you get the same homotopy groups. This is relating one of them. So we have this ascending sequence of more and more general notions of K theory. And we also have the K theory of a stable infinity category. The version of the wall doesn't US not construction. And even this is construction due to Andrew Blumberg, David Gebner, and Tabuada. I need to tell you a little bit about this, but not too much. So infinity category is a topological category. In other words, the objects are discrete. Morphisms. Topological spaces. And this is a notion which is due to many people. For example, Reiner wrote, but the main description of this is due to Lurie, Jacob Lurie, and he has a big book about it, which is going to take you a while to read. And it's stable. These are push-outs. The same thing as pullbacks. So examples of this. Is the key theory of a topological ring, especially the infinity ring, like the key theory of the sphere. And they're in complex numbers. KU of X. Key theory of vector bundles. On X. So the K-theory of vector bundles is the object of vector bundles, and the maps between them are naturally topological spaces, so this is an infinity category. This construction goes back to the beginning of time, where if you take a vector bundle, a projective module with complex numbers, that's a vector space. Whoops. Messed up. And K of X, where X is over the complex number. So you take a vector bundle on a variety, X, complex variety. You can topologically think of a corresponding vector bundle over the topological space X of C. And you get a natural map from the algebraic K-theory of X. The topological K-theory of a point. This is equal to Z 0. This is where n is even. This is where n is odd. And it gives you some sort of a starting idea of calculations. So this is the whole, all its glory, or the various versions of K-theory people talk about. And many of the talks will just focus on the K-theory of a ring, the K-theory of a variety. But occasionally some talks will talk about the K-theory of a fancier object, like one of these. I would normally ask for any questions, but the audience is virtual. So if you have a ring R, you can map R to the polynomial ring in T or the polynomial ring in T inverse. You can both include both of those into here. So there's various conventions with signs, but let's see, put a plus sign and a minus sign here, and then a plus sign here. So this defines a sequence, and then the co-kernel turns out to be Kn minus 1. And this formula can be used to define the K-theory of a ring in negative degrees. And one of the vanishing theorems that have been proven in the last couple of years is that the K-theory of the ring in negative dimensions vanishes below the dimension of the ring. And there's various versions about what happens exactly at the minus dimension. But so this is So negative dimensions of the K theory of the ring is the homotopy groups of the non-connected spectrum. Maybe I should say some words about what a non-connected spectrum is. You see that I'm going to have to crouch. Okay, a spectrum is a sequence of topological spaces, which usually people will use the letter E for, together with these maps. And the homotopy groups are going to be the homotopy groups, are going to be the direct limit of the homotopy groups of decay. So if you take pi minus 2, for example, you don't, you would sort of take pi minus 2 of this, pi minus 1 of this, pi 0 of this, pi 1 of the next one, and so on. So you sort of ignore the first two terms when you're taking the homotopy groups. Okay, so let's see here, where are we? I'm talking about the K30 field. The first fact, okay, finding a field of Q elements is something which is calculated by Quillen. And if you have an even number, it's this. And so the integers modulo Q to the I minus 1 is the same thing as is the same thing as the roots of unity of the field of QI minus elements. And there's a Galois action on it where the Galois group is acting on the field. So if you take Kn FQ bar is morphic to all roots of unity of FQ bar. But n is equal to 2L minus 1. Normally, put a parentheses I on there to indicate that the Galois group is acting not in the usual way, but it's acting according to the twist. So when n is equal to 1, there's no twist going on. But if n is greater than or equal to 1, for example, K3 or K5 or K7, then you start having the Galois acting in a different way. So what this means is that K3 of FQ is equal to K theory of FQ bar, G invariance, or G is equal to the Galois. we borrow the key. And all this calculation done by Claude. And the reason I'm bringing it up is it shows us a sort of an arithmetic nature to what's going on, in spite of the fact that this looks like a topological calculation, given all of what I did up here. Second thing, if K is algebraically closed. K algebraically closed. Characteristic 0. So the K theory is Z in degree 0, Q mod Z plus a uniquely divisible group in N equals 1, 0, whoops. Let me try this again. Z of N is equal to 0. Uniquely divisible group of N is greater than or equal to 0 and even. Is Q mod Z. Galois twist plus uniquely divisible group. Or N is odd. Okay, so that's the K theory of algebraically closed fields. Now I better not write any lower than that, so let's. And let me erase. My belief is that erasing is going to make the blackboard harder to read. So some of the people who are giving talks in the next couple of weeks are going to be talking about K theory of rings and varieties. Some of the people will be talking about the K theory of stable infinity categories. And I just wanted to give you sort of an idea about the fact that they're all sort of interconnected. And if you have a ring, you think the spec of the ring is a variety, then you can take this construction and you'll get the same homotopy groups. And if you take a ring and you think about it as chain complexes, you get the homotopy groups, you get the same result, or this result. Take a ring and you think of it as a stable infinity category, its K theory is going to be the same as all of these. So this is a successive wave of generalizations of the notion of K theory. So if you're just a beginner, you want to think about the K theory of vector bundles and the K theory of rings. But if you go and listen to the talks, you'll hear these other vocabulary lines. Okay, so back up a little bit. Suppose X variety. Combine the Chow groups of X. So it's a group of divisors. 3 billion. on the subarrays. Codivision I and rational equivalence. So what rational equivalence is, here's a picture of X. You have a function which gives you a map to the projected line. Here's 0, here's infinity. Here's what's happening at 0, and here's what happened at infinity. And F inverse 0 equal to F inverse infinity. So the slogan here is that 0 equals false. So the Chow groups are classical objects. And theorem called Riemann-Roch theorem. It has many incarnations, none of which look like any of the others. Basic theorem is K0 of X with Q. These are the next sum of the Chow lines. In other words, this is a notation on K0 of X. These are C gradients. Functions. The Chow I. And their Chern classes. Yeah, take K0 X. And the two-ith cohomology of X coefficients in Z. Well, being too fancy. So these Chern classes, these give you basically a connection between Chow groups and K theory and the composition. Roughly speaking, that what you lose is a factor of I minus 1 factorial torsion. You take the maps between here and here, the maps between here and here. So that when I tensor with the rational numbers, these torsion groups go away, and so we get nice morphism. This is going to come up in connection with motivic homology, which is going to be my next lecture on Wednesday. I just wanted to emphasize that this is what's going on. What are the tools? Yeah. So the main tool is that if U is contained in X, it's open. And Z is equal to the complement. You get I didn't say this. P theory of X, P theory of the projective angles, incrementals on X. P prime theory of X, and P theory of covariant X angles. And if X is smooth, P of X, something to P prime of X. Now, because when you're writing on a blackboard, little primes like this get buried in the back of erasing. We nowadays we write g of x, k prime of x. And the g is supposed to honor root d. So in order to make this clear, I'm gonna write k of x. K of x. Isomorphism. Well, it's a homotopy equivalent of spectral, which gives you an isomorphism on homotopy groups. So right after the k is equal to r mod equal log x equals kn plus 1. Okay. Undermapped kn of k plus 1 of f, k plus 1 k, kn of r, kn of f. Just boundary map again. Kn minus 1 of k, etc. What are the maps here? Map from kn minus 1, k area of r, k area of f, from vector bundles on r. Oops. Well, I'll say vector bundles on r. Vector bundles on f. Those are just vector spaces. Right. And the map from either of k, either of r. Is really the map of k, of r, to k modules. My modules. R modules. And so there's a conjecture which is Gersten. That is the map. Breaks up. Sequence of things which are 0. And R. And F. And minus 1. Okay. 0. This conjecture is known in any kind of situation where you have control over things. So, for example, integers over number field, the DVR associated with the integers over number field, or something which happened where R is a coordinate ring of a variety over a field. In those cases, it's known that this is an open conjecture. And as long as I'm There's a bias condition which says a bar is finally generated in the algebra. What we want to say is that each K in the bar finally generated within groups. And again, this is known in good cases and geometric cases, but it's open in general. So, as long as I'm at it, here's Parsons conjecture. It's not equal to 0. X is smooth. Refined field. The question is whether or not K and X are working. There are lots of questions which deal with K theory, very, very simple basic objects.
You want to say about Z? On Z, not, and you, when you say tools, on Z.
He intended to talk about.
There's two Z's here. Are you talking about this Z? Or are you talking about this Z? The ring or
No,
the,
but then there is no statement about Z, there is on X. I just wonder. Should it be
He
G or
intended
Z?
to write a localization C. Wrote it in the example.
yes. So the reason for mentioning this is that it's this map. This map is K(n) of X. K(n) of X is isolated to Gn of X. And Gn of K. And that's the Gn R. In order to Kn of R. So this particular map comes in this particular construction. That's, I'm sorry, I didn't write that down before, is that make it clear?
Z has become that.
So this was an example. So let's see if I can verify it again. Map. K of Z. K of X. Is it smooth? Is from K of Z as more than K. I'm using another Z. So let's see if U is open, is this next smooth? So if you're in that situation, this is so you get this long exact sequence. You this long exact sequence, which looks like that. And I specialize to the case where X is a DVR, I get this sequence. And the conjecture is that if it's a DVR, then it breaks up the, these values are 0. And that's what I was doing over there. So sorry about that. I'm talking about the connection to number 3. F is going to be a number field. In other words, a ring which is a field which is finally generated with ring of integers. Oh, if I take spec of R, the above setting, and then Z would be the disjoint union. The spec of R on P. Or taking the height on primes. And I get a localization sequence. Term on P is an order to the field of Q elements, some Q. We know the K theory of these guys. Question is what's related to the K theory of the other ones? And so the first thing is going to whoops. First thing that we know is that the K theory of R, 0 Q, use K theory of F, 0 Q. The calculation of rho. Oh, I'm gonna get, let's see, that's better equal to 2. So I'll give myself into trouble. 0 and is even. And it's C to the number of row 1 places. Sorry,
Q ratio, you tensor to Q.
sorry,
Since you tensor to the rationals, it's Q rather than Z.
yes. Um, You think this might. Always doesn't make much sense. And then it's zero elements. I said that up here. We also know that these are finally generated. So actually. These are the R1. The R1 comes up with origin. Origin. Question is, find the generators of these affinity groups. So if it takes Z to the R1 and I embed it in Q to the R1, then I want to know what the generators are. This is an open question.
Chow, your A should be modulo 4 there. Right? And it should be Q to R1 and 3 modulo 1.
No, you're right. So let's see. That's right.
That's 3 mod 4. But it should be Q to the power R2.
R2. This is n equals mod 4. No. Right? So the regulator maps. Very on my ring, which is R. The regular maps, there's a huge industry in this. Again, as I don't emphasize, we still don't know what the generators of this are. And that's just a sort of a circle ideas that come up with number things. Now, there's another conjecture which is abundant, and that's the von Neuer's conjecture has to do with the third group and join pieces of unity. This is a conjecture which goes back to Kummer. (1858). Invented circa 1920. And it specifies that either the integers is equal to 0 when n is congruent to 0.14. Okay. Or n, I'm gonna say 20,000. I've heard a rumor that it goes, you can go up to 100,000 now. This is all done with computer calculations. The Adams operations are certain operations which go from the K theory of R to the K theory of R. And K theory of R, the Q. Negative space. K theory of R. Q. Is more of a direct sum. K n of R. Is it Q? N, this is not an N, so there better be some other letter. The direct sum of I. And then the vanishing conjecture. Is it the K? And then R. Is it the Q? Negative. 0. And this is not on. Here goes right. I just I got it backwards. I just no, because I switched to I had already first time.
Could be no weight.
Nothing in low weights, so let me write down the example that I was going to give, and then we can figure it out. Here's I equals to 2. A equals to 5. So it's I. Ready. You get it right now. This is totally open. This is related. Okay, cohomology. And has to be what's going on for next time. So that's the circle ideas about what K theory is and what we know about them and what are some of the open conjectures. So thank you very much. Thank you for correcting me on my subscripts. Right?
No questions, so we'll thank the speaker.
This must be answering it there.